is Joel Gardner, and he got both the best paper award and the best student paper award. So quite a remarkable achievement. And he's going to be our first speaker. So I'll let you take it from here. Thank you.
Is it working? No, it's working. Thanks for the introduction, and I'm very grateful for having received these awards. So in this work, I have developed a new lattice-based Fiat Shamir with aborts signature scheme. And this new scheme is significantly more compact than previous comparable alternatives. And as you can see in this table here, we have a signature size, which is less than 1/3 of that of the lithium, and that combined verification key and signature size, which is less than half of that of the lithium. And this new compactness is enabled by a new reaction sampling method and a new iterative signature construction. And our new methods also allows us to parameterize our scheme so that we can actually ignore, in a secure way, the aborts part of the Fiat Shamir with aborts paradigm, while keeping the scheme very compact. And although it somewhat decreases the compactness, it still results in a scheme significantly more compact than previous comparable alternatives. And the Fiat Shamir with aborts paradigm is the basis behind the lithium, which has recently been standardized as MLDSA by NIST as a post-quantum secure signature scheme. And the origin of this types of signature scheme is with a signature scheme by Lyubashevsky, which essentially can be seen as a lattice-based variant of the classical Schnorr signatures. And these lattice-based signature schemes rely upon the assumed harness of the SIS, or short integer solution problem. And for Lyubashevsky's signature scheme, the private key consists of a matrix S with short columns, whereas the public key contains a random matrix A and a matrix T, which is given as AS modulo Q. And to sign a message mu in this signature scheme, you begin by sampling a short vector Y and use this to derive a short challenge vector C by using a random oracle that you feed with A times Y modulo Q and the message mu that is to be signed. And a signature is then given by this challenge vector C combined with a vector Z given as Y plus SC modulo Q. And as Y is a short vector, S has short columns, and C is a short vector, then this Z vector is also, in expectation, a short vector. And to verify a signature, you verify that Z actually is a short vector, and you verify that the challenge vector C can be recomputed in the expected way, which is possible to do like this, because for valid signatures, AZ minus TC is congruent to AY modulo Q. And as presented, this scheme is, however, not secure because every signature leaks some information about the secret key. And this is the case because the signatures contain the Z vector, which is given as Y plus SC, and it therefore follows a distribution that's dependent on secret information. And if an adversary collects many signatures, they may therefore be able to recover part of or the full secret vector, secret matrix S. And Lyubashevsky's solution to this problem is to not always emit the constructed signatures, and instead sometimes aborting and restarting the signing attempt with new randomness. And this abort and restart corresponds to reaction sampling from the distribution of Y plus SC to get something from a distribution that's independent of secret information. And this reaction sampling can quite nicely be illustrated in one dimension. And this one-dimensional illustration is actually quite illustrative of the higher dimensional case, because everything basically projects down into the direction of SC. So in one dimension, or we focus on the case where Y follows a discrete Gaussian distribution. So the probability of a specific Y is proportional to a Gaussian function illustrated here in blue. So in one dimension, Y follows a Gaussian, one-dimensional Gaussian like this, and SC is on shift. So Y plus SC is follows a shifted Gaussian distribution with this shift depending on secret information. So to ensure that signatures do not depend on secret information, we reaction sample from a centered Gaussian distribution, illustrated here in red. And to do this, we simply emit a constructed Z vector with a probability that's proportional to the quotient between the Gaussian or the desired output probability and the actual probability of constructing this Z vector. So this is given by this quotient here, where we also include a reaction parameter M in order to ensure that this quotient is essentially always upper bounded by 1, so that we can use it as a probability. And this corresponds to the red curve fitting under the blue curve. And for parameterizing this type of scheme, there are some different trade-offs. And we would like to use as small of a Gaussian parameter as possible, as this would lead to a shorter Z vector, which would lead to the security of the system relying upon a harder version of the SIS problem. Additionally, a shorter Z vector leads to a more compact signature, because a shorter vector can be more compactly represented. However, decreasing the Gaussian parameter leads to a higher reaction probability and therefore to a less efficient scheme due to requiring more restarts. And because of these trade-offs on the Gaussian parameter R, we have that if we create a better reaction sampling method, this may improve many different aspects of the scheme and not only the efficiency of the scheme. And as an example of this, we have the bimodal reaction sampling that was developed for the Bliss signature scheme, where they used a different public key construction to allow the signatures to be given as with a Z vector that's equal to y plus or minus SC, with the Bliss selecting both of these options with equal probability. This leads to the Z vectoring following a bimodal Gaussian distribution here in blue, and it's then possible to reaction sample from the red centered Gaussian distribution. And the benefit of this bimodal reaction sampling is that it's possible to handle much larger shifts SC with the same reaction probability, or by the trade-offs previously mentioned, to handle a shorter Z vector with the same shift, leading to a more compact scheme. And the idea behind our new reaction sampling actually follows quite naturally from a reformulation of the bimodal reaction sampling of Bliss. So typically, the reaction sampling of Bliss is formulated as you first having a Y vector, and you're constructing a Z vector as Y plus SC or Y minus SC with equal probability 1/2. You then accept this constructed Z vector with some probability R of Z or some reaction function R. These two steps can be reformulated into a single step, where we are given a Y vector, and we then construct a Z vector with probability Y minus SC with some probability f of Y, and as Y plus SC with some probability g of Y, with these functions f and g given like this. And it's then quite natural to wonder if we have more general functions, f and g of Y, that we can use for this purpose. So where we construct Z as Y minus SC with probability f of Y, and as Y plus SC with probability g of Y. And in particular, for our work, we consider the case where the input Y follows a discrete Gaussian distribution, and thus the probability of a specific Y is proportional to a Gaussian function rho R of Y, which has a parameter R. And we want the output Z to follow the same distribution. And we can consider the probability of constructing an output Z via the f function, which gives this function f of Z, and via the g function, which gives this function g of Z, because we have to take into account the probability of constructing a specific Y vector and the probability of using the g or f functions, respectively. And to have the correct output distribution, we then simply require the sum of these functions, f of Z plus g of Z, to be a scaled Gaussian function, which we can see to be the case for our reformulation of the bimodal reaction sampling of Bliss. So now our work, we developed new functions, f of Y and g of Y, which also can be used for this purpose. We won't go into detail on how we actually construct these, but the end result is functions that look like this, where we note that both f and g of Y are defined in terms of this infinite sum s of Y. And a worry might be that we can't compute this infinite sum efficiently, but we show that in the relevant regime, we can actually approximate this sum sufficiently well by just including a few terms of the sum. Noteworthy here also is that the functions are defined with this reaction parameter m, and this has an important impact on the efficiency of the scheme, as in expectation, the designing attempts will react with probability 1 over m. And the reason we need this reaction parameter m is to ensure that f of y plus g of y is always upper bounded by 1, so that we can use these functions as probabilities. And to actually select this parameter m, or this parameter m, is directly determined based on another parameter, alpha, which is upper bounded by the maximal value, which is upper bounded by the minimal value that R over the norm of SC takes for our scheme. And as with Lyubozhetsky's signature scheme and with Bliss, we can provide that one-dimensional illustration of the reaction sampling for our scheme. And as you can see, the function f provides a somewhat more complicated redistribution of probability compared to the function used for Bliss. And the function g provides a symmetric redistribution. And we have that the sum of f of y plus g of y is always lower than 1, and at most almost exactly equal to 1 due to us selecting the m parameter in a good way. And we can also consider the probability of constructing a specific z vector via the functions f and g, giving these functions f of z and g of z, respectively. And we then have that the sum of these functions is a scaled Gaussian function as desired, meaning that we get an output that follows a centered Gaussian distribution, which is independent of secret information. And for the performance of the scheme, we can, or for the new reaction sampling, we can compare it to the reaction sampling of Bliss, or the bimodal reaction sampling. And as with our scheme, the reaction sampling of the bimodal reaction sampling also depends on a parameter alpha, which is upper bounded by R over the norm of SC. And for Bliss, they use a parameter alpha that's between 0.5 and 1, corresponding to a repetition rate, which is between 7.4 and 1.6. And here to the right, we have the logarithm of the expected number of reactions for the bimodal reaction sampling of Bliss as a function of alpha plotted. And here in red, we have the behavior of our new reaction sampling. And we would desire, or it would be good if we could use a smaller alpha for our new reaction sampling, as this would allow for a more compact scheme. But as you can see here in this plot, for smaller alpha, our reaction sampling and the one of Bliss behave almost exactly the same, or very similarly. And the benefit of our new reaction sampling is instead that we can use, or we get a much lower reaction probability when we use a larger alpha. However, by itself, this is not that interesting, at least not from a performance perspective, because the difference in performance of reacting every 100th signing attempt and every 1,000,000th signing attempt is not that big. So instead, to gain a significant benefit of our new reaction sampling, we develop a new iterative signature construction, which is possible thanks to the fact that the public key construction of Bliss actually is more flexible than I previously mentioned, and actually allows signatures to be constructed with a z vector that's equal to y plus sc prime, for any c prime, which is congruent to c modulo 2. And this allows us to iteratively select the signs of the challenge vector c, which is a 0, 1 vector, allowing us to perform reaction sampling on the columns of the secret matrix S instead of on the full SC vector. So the basic idea behind this iterative reaction sampling is then to let, can be described by letting Z0 be equal to Y, so the input. We then iteratively construct Zi as Zi minus 1 plus or minus SiCi, with this sign then being determined by our new reaction sampling method. And if any of these iterative reaction sampling steps fail, then the full reaction sampling fails. But if all of the steps succeed, then every Zi follow a discrete Gaussian distribution. And in particular, this includes Zn, which is given as y plus sc prime for some c prime congruent to c modulo 2. And thus we can use this Zn for our signature. And the benefit of this iterative signature construction is that we perform iterative or reaction sampling, where each iterative reaction step uses reaction sampling with a much larger alpha, which is now only upper bounded by the Gaussian parameter R over the norm of a column of the secret matrix. The downside is that all iterative steps must succeed at the same time. But this is more than made up for when we use our new reaction sampling method, as the reaction probability for our new reaction sampling decreases very quickly as we increase alpha, allowing us to have this performance here in black for our new iterative signature construction. And as you can see, it allows for significantly smaller alphas to be used, leading to allowing us to construct a more compact scheme. And to illustrate the compactness of our new scheme, we developed a concrete signature scheme. And to allow for the most compactness, we consider a scheme based on a structured lattice problem. And we could base the scheme upon the entry problem or the MLW problem. Basing it upon the entry problem would lead to a somewhat more compact scheme, whereas basing it upon the MLW problem would have the benefit of leading to a scheme that's somewhat more flexible to parameterize. Instead of basing our scheme on one of these more standard problems, we base it upon the MTW problem that was introduced a couple of years ago as a natural combination of the entry and MLW problem. This allows our scheme to have the flexibility to parameterize as an MLW-based scheme with the compactness of an entry-based scheme. And the MTW problem is quite similar to the MLW problem, where we have a secret vector S and a error vector E, and work in some polynomial ring with some dimension n. And additionally, and similar to the denominator in an entry instance, we have a secret invertible element F. And in the decision version of the MTW problem, you're given an A matrix, which is uniformly random, and a B vector that's either uniformly random or equal to AS plus E, with all of this multiplied by F inverse. And the task is to distinguish between these two cases. And a worry might be that this MTW problem is relatively new and untested, and you might want to rely upon a more standard problem. And this leads to, so an alternative is to have an MLW-based scheme. And this leads to a somewhat less compact scheme, but it only increases the signature size by about 300 bytes, or at maximum 300 bytes. And this still results in a scheme that's significantly more compact than previous Viet-Shamir-based lattice schemes. And for comparing or illustrating the compactness of our scheme, first, we have, for our concrete scheme, we use a dimension n equal to 256 for our ring, and the modulus q, which allows for efficient operations to be performed using the number theoretic transform. We also use various standard tricks for compressing the scheme, such as replacing a large part of the signature with a hint vector and using efficient encoding methods for the signature. We also propose two different variants of our scheme, one which has a reaction probability rate of about 50%, leading to a more compact scheme, and with this reaction probability being comparable to that of previous schemes. And another one which has a reaction probability of less than 2 to the minus 100, allowing us to securely ignore this reaction probability, leading to a scheme without reactions. And for comparing our scheme to previous scheme, we have this plot here with the signature size on the y-axis and the verification key size on the x-axis. And first, we have here the three different security levels for dilithium or MLDSA. And these can be compared to the compactness of the same security levels for HiTi, which uses bimodal reaction sampling to allow for a more compact scheme. And compared to HiTi, our scheme is significantly more compact. And here is our scheme with reactions, leading to the most compact version of our scheme. And even our scheme without reaction is significantly more compact than HiTi. And our scheme with reaction is significantly more compact than the previous Viet-Shamir-based lattice schemes, and instead has compactness that's quite similar to Falcon, included here with the blue triangles, which there is only 2 security levels corresponding to the highest and lowest for Falcon. And Falcon is also in the process of being standardized by NIST. It is based upon the hash and sign paradigm. And a big reason why NIST has decided to not only standardize the more compact Falcon is that it actually seems, and instead also standardized Dilithium as MLDSA, is that it seems to be quite hard to implement Falcon in a secure manner. And our hope and belief is that for our new scheme, our new scheme can be implemented in a secure manner, can be easier to implement in a secure manner. Compared to Dilithium, there are, however, some downsides in terms of implementation complexity for our new scheme, in that, firstly, it's previously proven to be non-trivial to perform reaction sampling from Gaussian distributions. Additionally, our new method for reaction sampling may somewhat complicate implementations. However, we also have a benefit compared to Dilithium in that we can easily parameterize our scheme so that we do not have to perform reactions at all, which may simplify implementations. So, in conclusion, we have developed a new method for reaction sampling, which enable us to construct a significantly more compact lattice-based Viet-Shamir signature scheme. And due to it potentially allowing for simpler implementations, we consider it a very interesting open question if a similar method could be used to improve reaction sampling from uniform or some other distributions. And finally, I have this table here with some sizes for our scheme and other lattice-based signature schemes, which I figured I could leave up while I can answer any potential questions. Thank you.
Any questions? No. Okay. Oh, did you have a question? You good? Okay. Okay. Thank you very much. Thank you.